Dear student, welcome to the second lecture of linear algebra. In the first lecture, we have seen definition of a vector space and its subspaces with some examples. In this lecture, we start with definition of homomorphism from vector space U to V. Here, if U and V are two vector spaces over a field F, then the mapping defined from U to V is said to be homomorphism if the number one condition is u1 plus u2 operated by t is equal to u1 operated by t plus u2 operated by t. It means t must preserve the addition operation in u to v. The second condition is alpha into u1 operated by t is equal to alpha into u1 operated by t. In this case, t must preserve the scalar multiplication in u to v. Now we consider one example of homomorphism. Let t from R3 to R2 be defined as t of alpha 1, alpha 2, alpha 3 means the element in R3 and its image is the element in R2, that is alpha 1, alpha 2. Then it is easy to show that this t is a homomorphism. Then for v1 is equal to alpha 1, alpha 2, alpha 3 and v2 is equal to beta 1, beta 2, beta 3 in R3, we operate t on v1 plus v2 is equal to the addition of two vectors in R3 gives us alpha 1 plus beta 1 is the first component, the second component is alpha 2 plus beta 2 and third component is alpha 3 plus beta 3. And when we operate it by t, by definition it will give you the ordered pairs. First component is alpha 1 plus beta 1 and second one is alpha 2 plus beta 2. Again, by definition of addition in R2, we write as is equal to alpha 1 alpha 2 plus beta 1 beta 2, and then by using the definition of t, we write this as v1 operated by t plus v2 operated by t. It means t preserves the addition. Now we consider real number lambda, then lambda into v1 operated by t is equal to, again by definition of scalar multiplication, lambda into v1 is lambda into alpha 1, lambda into alpha 2, lambda into alpha 3, and this triplet is in R3, and when we operate it by t, it will give you this by definition lambda into alpha 1, lambda into alpha 2. Again, by definition of scalar multiplication in R2, we write it as lambda into vector alpha 1, alpha 2. Again, we replace this by definition of t, it is lambda into v1 operated by t. So we say that t from R3 to R2 is a homomorphism. Note that if t is 1 1, then t is called an isomorphism of u into v, and that if u and v are said to be isomorphic if t is an isomorphism of u onto v. Now we define kernel of this homomorphism. Kernel of t is equal to set of all vectors u in capital U such that u operated by t is equal to 0. One may easily verify that kernel of t is a subspace of U. Now we consider definition of internal direct sum. Let V be a vector space over F and u1, u2 and so on un be its subspaces. Then V is said to be internal direct sum of its subspaces u1, u2 and so on un if every element V in capital V can be written in one and only one way as V is equal to u1 plus u2 and so on un, where ui's are in capital UI. For example, let w1 be set of all vectors a0 such that a belongs to R, and w2 be set of all vectors of type 0b where b belongs to R. We know that these two are subspaces of R2. Then every element, this ordered pair AB in R2 can be uniquely expressed as ordered pair AB is equal to U1 plus U2, where U1 belongs to W1 and U2 belongs to W2. That is, if ordered pair AB belongs to R2, then ordered pair AB is equal to the vector A0 plus the vector 0b, where the vector A0 is in W1 and 0b is in W2. Thus, every vector in R2 can be uniquely written as sum of two vectors. One is in W1 and another is in W2. We say that R2 is an internal direct sum of its subspaces W1 and W2. Also note that W1 intersection with W2 contains only one element, that is 0, 0. Now we consider definition of external direct sum. Given any finite number of vector spaces V1, V2 and so on Vn over a field F, let this n tuple be an ordered n tuple in V where Vi are in capital Vi. Two elements in V are equal, that is, the n tuple V1, V2 and so on Vn is equal to the n tuple V1 dash, V2 dash and so on Vn dash are equal if and only if they are component wise equal. That is, V1 is equal to V1 dash, V2 is equal to V2 dash and so on, Vn is equal to Vn dash. And that if we add two elements in V, then addition is defined as V1, V2 and so on Vn, the first n tuple, and we have second n tuple in the space, then their addition is in this way. Then the scalar multiplication is defined as alpha into the vector V1, V2 and so on Vn is equal to alpha into V1, alpha into V2 and so on, alpha into Vn. So this is the scalar multiplication in V. Then this V itself is a vector space over F, and this then V is called the external direct sum of the vector spaces V1, V2 and so on Vn. And in this case it is denoted by V is equal to V1 direct sum with V2, direct sum with V3 and so on, direct sum with Vn. Clearly Rn is a direct sum of R, that is, Rn is equal to R direct sum with R and so on, direct sum with R n times. Note that if V is the internal direct sum of its subspaces U1, U2 and so on Un, then V is isomorphic to external direct sum of the spaces U1, U2 and so on Un. Finally, we consider definition of linear span. If S is non-empty subset of a vector space V, then L of S is called as a linear span of S if L of S is a set of all linear combination of finite set of elements in S. That is, L of S is set of all linear combination, that is alpha 1 V1 plus alpha 2 V2 and so on, alpha n Vn, where alpha i's are the scalars in the field F and Vi's are vectors in S. Clearly, L of S is a subspace of a vector space. Also, if S and T are subspaces of vector space V, then if S is a subset of T, then L of S is also subset of L of T. Now, in this case, we say that they are subspaces. Also, if we consider a linear span of a set, then it will give you same space linear span, that is L of S. And that linear span of S1 union with T is equal to linear span of S plus linear span of T. Now we consider one example of linear span. Let S1 contains only one vector, which is 1, 0 in R2, therefore S1 is a subset of R2. Then its span is L of S1 is A into 1 0 where A is in R, and therefore the elements are A0 where A is in R, and S2 contains only one vector, that is 0 1, which is also subset of R2, then its span is set of all ordered pairs 0b such that B is in R. And now if we consider S3, which contains two elements, one is 1 0 and second one is a 0 1, then in that case, if we consider its span, then its span is A into 1 0 plus B into 0 1 such that AB belongs to R. It means it is the ordered pairs AB such that AB belongs to R, and obviously this must be equal to R2. Thus, linear span of S1 gives us the whole real axis, whole x-axis, and the linear span of S2 will give us this whole y-axis. Okay, and then finally we have this S3, which contains the ordered pairs 0 1 and 1 0, and if we consider its span, it will give the whole space R2. This space R2, which is a linear span of this S3. Students, in this lecture we have seen the definition of homomorphism, internal and external direct sum, and linear span with some examples. In the next lecture we are going to see the definition of linearly dependent and independent vectors, then basis of a vector space, and third point is a dimension of a vector space with some examples. Thank you.